We know that forces can cause not only translational motion, but also rotational motion. For example, we all have the experience of using a wrench to loosen a screw. When we apply a force on the handle, we can cause the screw to rotate. We also know almost intuitively to apply the force at the edge of the handle, creating a maximum distance from the screw. And why is that? What would happen if we shorten that distance, say by half? From experience, we know we must apply a bigger force now in order to create the same rotational effect on the screw. In fact, we need to double that force. Apparently, there's a certain quantity that needs to be achieved in order to loosen that screw. Therefore, moment is defined in order to quantify this rotational effect caused by a force about a certain axis. In this example, the axis is perpendicular to the plane, and you can imagine it as an arrow shooting out from point O, and you can only see the head of the arrow represented by a dot. Sometimes a moment is also called a torque. And just like force, moment is also a vector and therefore follows all vector calculation rules. To better understand the moment caused by a force, let's imagine there's a force F in the xy plane, shown in top view and side view respectively. You want to find the moment caused by this force about an axis z, which is perpendicular to the xy plane. This axis z intercepts the xy plane at point O. However, from the top view, you will not be able to see the z-axis, so again, just imagine an arrow shooting out from point O. The rotational effect caused by the force can be determined by the right-hand rule, which means that if you extend the 4 right-hand fingers from the axis towards the force, and then roll the fingers to the direction of the force, your thumb will point towards the direction of the moment vector, noted by mz, indicating it is a moment about the z-axis. And the rotational effect is always counterclockwise about the moment vector, also agrees with the rolling of your 4 right-hand fingers. Again, from the top view, you will not be able to visualize the moment vector since it is like an arrow shooting out of the plane, and therefore you can only see the head of the arrow. Therefore, for a 2D problem, the rotational effect can be considered to be within the plane about the point O. Therefore, the moment mz can also be expressed as mo. Now you know the direction of the moment vector and also what rotational effect it represents. How about its magnitude? Just like the force, the moment vector can also be quantified, and its magnitude is determined by the magnitude of the force, as well as the perpendicular distance between the axis and the force, d, known as the moment arm. So in the scalar form, m equals to F times d, and in the vector form, the moment is determined through vector cross product that m equals to r cross F, with r being the position vector from point O to F.